Alright, hey guys, what's going on? So today we are going to get into understanding expectation values in terms of the Gaussian integral, and we're also going to be able to understand sources or source terms by the end of this as well. This is all within the context of quantum field theory. And so with that being said, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support there, or you can support by becoming a member here on YouTube. So with that being said, let's go ahead and get started. So what we're going to do today is we're going to look at or understand source terms, right? So source terms are these things that we talked about earlier that move our Gaussian integral around, okay? These are things that are associated or are going to be associated with how we probe our systems, okay? When we're measuring interactions within a system or something like that, we typically do that by probing the system with some source, and that source term is going to move our Gaussian integral around. And what we came across yesterday, or not yesterday, but a few days ago, was the idea that these source terms are going to move the Gaussian around. That Gaussian, as it moves away from the center, or from the origin of our coordinate system, over state space, it's going to, the peak of that Gaussian is going to get higher, okay? And so that, the peak of that Gaussian, or the peak of that Gaussian is going to resemble something like moving around the quantum fluctuations, okay? And we'll see why this is the case. This is the equation that I want to get at for those of you who are not contributing and contributing to the channel, because this is sort of the main point I want to get across. The idea here is that we're going to construct an equation, okay? We're going to construct this seemingly arbitrary equation that, or such that when we take sequential derivatives of it, we get these numbers out, and these numbers correspond to expectation values of a time-ordered series of events, okay? And this, the example I have here, we'll go to the beginning of this slide in a bit here, is that, well, so, okay, suppose I have a function that looks like this, okay? And the derivative of this function will be a of n taken when x of n is going to go to 0, okay? Here, when x goes to 0, we get the coefficients back, okay? And these coefficients are going to tell us something about the expectation value of a time-ordered series of events when it comes to quantum states, okay? All right, so let's go here and let's get started. Okay, so in the last video we covered the Gaussian integral and how they are interpreted within the context of these linear source terms. We found also that the linear terms contributed to a shift away from the origin. However, there was a cost in the linear term that scaled the Gaussian integral. That cost, so here is our original Gaussian integral. The shifted Gaussian is going to be as a consequence of these j terms, and these j terms are these are the source terms, okay? So this is what we established last time, all right? In quantum field theory, we are now going to make a leap, and we're going to make a proposition here. This proposition is going to be, well, here's our Gaussian integral, all right? And we are going to say, well, so we established this last time, this equation right here. This equation right here told us that we could take our Gaussian, or our source terms, and write them in this way, right? So this is going to be a representative of the shift in our Gaussian, right? So our Gaussian is, or the spread of our Gaussian is going to be represented by the coefficient values in A, right? So we can think of A as a matrix, right? So A, the thickness of my pen, change that to 1, much better. We're going to have A sub 1, A sub 2, A sub 3, and so forth. So A is a diagonalizable matrix. So diagonalizable matrix. All right. And that diagonalizable matrix is right here in this exponent, which is integrated over in in space, and we have the small interval in which we're making this, in which we're doing this measurement, right? So, not really a measurement, right? This is just the integral, or this is just the Gaussian within this small area, or this small volume. Okay, so this here is right here, which is, again, this is right here, right? I'm just highlighting a few things here, because when we take a look at this function now, this here is called the generating functional. This is the generating functional. The generating functional is this z of j. It's called a functional because j is a function, and so this is a function of functions, right? And so this here, so if it's a function of functions, that means it's a functional. Okay, that's the point. Okay, so this here we're defining to be our to be our Gaussian, right? This is our Gaussian, which is right here, and this takes a very similar form. Right? We have our j terms, we have our fields, and then we have A, which is our diagonalizable matrix. So our generating functional is really just a Gaussian integral. Well, you might think, okay, why are we doing this? Well, why are we renaming this to this generating functional? Well, it's going to become clear soon that this thing is going to take on another very interesting form, such that when we take subsequent derivatives of it, we get this time order expectation. This expectation value for time ordering states. Okay, so step one. So step one here is, okay, we're making this leap. We're making this leap. We're proposing that this is our Gaussian. Our Gaussian looks, and this is we're calling this our generating functional. Okay, so z of j is like a Gaussian integral, but instead of summing over space-time points, we're summing over state or phase space. And so the generating functional is like a Gaussian over state space. Okay, simple enough. This means that we can imagine the peak of the Gaussian representing high probability of states, right? So wherever the peak is, right? So we can imagine we have our, that's a terrible Gaussian. We can imagine our Gaussian in state space, right? And wherever the peak is, so that's going to be associated with some states, right? And so it's going to be associated with like this state here and that state here. We can sort of think of it in this way, and when we shift this thing, the thing that does the shifting is our j terms, okay? And when it shifts, it we increase the height of this generating functional, or the expectation value. All right. So this means that we can, so imagines representing high probability states. The spread of the Gaussian A can be thought of as a differential operator, okay, that dictates the spread of the dynamics of the field over of the field that's over, and J can be thought of as representing an external source coupled to that field. Okay, it's coupled to the field because, again, it's being multiplied by the field itself. Okay, so the goal now is to incorporate the source terms into this path integral. Right, so we have the source terms here. We're going to aim to do this because we want to be able to probe the system, like we said before, at different points in space-time, and to know the effects of the action of this particle. Okay, the effects on the action or on the dynamics of this particle. action, when we say action, we mean the term S, right? So S is the action. And it's usually not a function, it's usually an integral over some volume, d for x, right, and so forth. This is our action. We want to know how these things, this source term gets incorporated into our action. And that's the goal here. Okay, so this is what we're going to derive in the end. This is this is again our state space Gaussian. Okay, that's this thing. When we take derivatives of it, subsequent derivatives of it, we get with respect to our functionals, then we get our time-ordered series of our time-ordered states, right? The n functional derivatives of the Gaussian integral will give us the types of dynamics for the quantum process, okay? And this is going to be sort of the leap into understanding a lot of quantum field theory, right? So we're talking about Gaussians for these two videos, and then we'll go into spinors, and then we'll start really getting into quantum field theory a little bit more. So it's possible to make sense of this intuitively to some degree. We can imagine that for every subsequent derivative of the Gaussian that we're able to take, we're probing Feynman diagrams of higher number of modes or higher degrees of resolution, if you want to think about it that way. So if we have one Gaussian, this is going to be our 1-point correlation function. This we'll define what correlation functions are later, but for right now, this is going to be our 1-point correlation function. This is going to be tethered to the idea of the vacuum expectation value. And when we look at a space-time diagram, it's just going to be the expectation value of some particle located at some state, okay, or having some particular state. For our 2-point correlation function, well, this is what our Gaussian looks like. What's interesting about the Gaussian, if you're not aware, is that subsequent derivatives of the Gaussian, right, just result in more continuous Gaussian-looking functions. In other words, there's no point at which there's no stopping point, right? You can take the nth derivative of a Gaussian, and you still get this very interesting continuous curve. Okay, that's something that's quite unique about the Gaussian, and it allows us to take mathematical. It allows us to sort of mathematically probe our system at higher and higher degrees of resolution. Okay, and the propagation. So this is going to represent propagation of particles, right? So we have particle gets propagated from one point in time and space to another point in time and space. Okay, so we have two nodes here, 2-point correlation function. A 3-point correlation function is going to correspond to elementary interaction vertices. Okay, and so at this vertex here, we have 3 things attached, right? We have particle traveling, but then there's also this interaction with, say, a gamma particle or something like that. So we're probing at higher degrees of resolution using these correlation functions. All right. So what the hell is a correlation function? Let's go ahead and get started on this. We're going to propose what our So here, this was our generating function. We're going to take a look at this a little bit more mathematically now. Let's propose the following function. This is a power series. Okay, the power series is this guy right here. It's 1 over n factorial times a to the n multiplied by n to x to the n, right? So if we take this function and, for example, just take the second derivative of this. Again, this is just an example. When we take the second derivative and evaluate it at x equals 0, well, the second derivative of our power series is the second derivative of this, right? Because this is just our power series. And sorry, I got a little something on the iPad there. so this is our power series. The second derivative of this thing is going to be this right here, right? Because we get rid of A0 and A1, right? Because these are not, we're taking second derivatives here. So these two guys are going to go away, right? Because the derivative of this, the second derivative of this is just 0. The first derivative is A1. Second derivative is just 0 because the derivative of a constant is 0. And so we're left with all these terms left over. So when we take the second derivative of this, we just get A2, right? Because we're going to get 2A2, or 2 over 2 times A2 as the first derivative. So that's just A2x as the first derivative. And then the second derivative is just going to be A2 because that's just a constant in front of x. Okay. We do the same thing with all the subsequent terms here. But the idea here now is that, okay, so we get all this. But now, when we take x to equal 0, everything behind A2 collapses down to 0. So now we just get A2. So the second derivative of f evaluated at x equals 0 is A2. So what we've been able to do here is we've been able to say, well, second derivative is going to correspond to second coefficient. Third derivative is going to correspond to third coefficient, and so forth. Okay? This is all made possible by, we could sort of think of this whole thing as an operator acting on f to give us A2. Okay? Okay, so this is kind of interesting. Let's make this a little bit more general. We say the nth derivative of f evaluated at x equals 0 is an, where n here is going to be, it refers to how many derivatives you're taking. Okay, so here's the leap, right? The leap is, okay, this is, we're going to call our Gaussian integral in state space, or generating functional. This here is going, or these guys here are going to be sources that move in space and time, so we can take derivatives of this with respect to source functions. And this here is going to be called our expectation value of a time-ordered series of events. These are the endpoint correlation functions, right? So let's just write those down. This is our generating functional. This here is our endpoint correlation function. And these are the source terms. All right. The power series identified here is the generating functional, and the coefficients are identified as the endpoint correlation functions. We can think of this, okay, so here's the point that I bolded here. We can think of this as when a source moves, okay, in space-time, it shifts the state-space Gaussian around, okay. So you could imagine probing a system that's going to shift our Gaussian around, and shifting that Gaussian around is going to correspond to different expectation values for different states as we do this probing. As the Gaussian moves around, its maximum point changes, which is represented by an expectation value of a time-ordered series of events. Okay. With this picture in mind, we can now begin our derivation here to better understand this. Well, first we need to see how the endpoint correlation function represents an expectation value. And the workflow is going to be as follows, right? So I like to, I decided to do this because it's very easy in quantum field theory, I feel like, to get lost in the weeds. So if we have a big general overview of how this is going to go down, then we can dive into the deep end a little bit easier, I think. So we're going to start off with defining an expectation value. We kind of know what that is going to look like already. We've talked about expectation values on this channel before, so that's not going to be too difficult. We're going to then rewrite it in terms of a path integral, or with the path integral. We're going to iterate the expectation over discrete time-ordered points. Right, so we're going to iterate this thing over a discrete time-ordered series of events. And then we're going to be able to define our correlation function. Okay. From there then, we take the power series. We're going to use this correlation function as coefficients in a power series over the source terms. And then we're going to rewrite the power series as path integrals within the sources, or with the sources. All right, so that is how this is going to go down. And the rest of this video then is going to be for those of you who are contributing to the channel. So if this is something you're interested in, go ahead and make sure to hit that like and subscribe button. And you can go ahead and make sure to go onto my Patreon page and contribute, or become a member here on YouTube and contribute here. So with that being said, I will see you guys in the next video. Bye.